Good morning and welcome to another edition of the Henstitute. Today we're going to talk about the difference between refraction and reflection. So last time we already dealt with reflection and the concept of the law of reflection is the fact that the incident ray is equal to the reflected ray. So if this is my incident ray of light coming in and it strikes this little surface here where the water and air meet, that this angle, theta 1, is equal to theta 1 over here. In other words, these two angles are equivalent because this ray of light is coming in, hitting this surface and reflected in this particular direction. And so we have an incident ray and we have a reflected ray. So that's our law of reflection, the fact that those two things are equal to each other. The other concept that we have is what is known as refraction. And so refraction really breaks down into this idea. So refraction is the bending of a wave as it goes from one material into another. Bending of a wave as it travels from one material to another. So in this particular case, what we have is we're going to have this air, and then we have water. And so as this incident ray comes in, I'm actually going to change the color. Let's make this purple. So as this incident ray comes in and it hits this, we know some of it's going to get reflected because if you've ever looked at a surface of water, we know some of the light gets bounced off of that water, but some of the light is also going to get refracted. In other words, it's going to go into the water. So it's going to travel in this particular direction. So what they're trying to show here with this theta 1 and this theta 2 down here is the fact, so theta 1 and theta 2 are not going to be equal to each other because you can see that this purple light that I've actually drawn has been bent. So this refracted ray shows that bending. Now, the reason this happens, if you notice over here, we have these little numbers over here, N1 and N2, and they've got 1 and they've got 1.33, and they're like, what in the world does that mean? So what they're talking about is the index of refraction is a number, these N numbers, which indicate the speed of the light compared to the speed in that material. So there is a concept known as the index of refraction. Index of refraction. And the index of refraction, usually labeled by a lowercase n, is equal to the speed of light in a vacuum. So that's basically our 3 times 10 to the 8th meters per second, divided by the speed of light in that particular material. So this is actually the definition of a thing called the index of refraction. So air usually has a value of 1. It's technically not 1 because c is actually the speed of light in a vacuum where there is no material. And the speed of light in air, for example, is pretty close to that. And so you get this ratio to almost be 1. It's actually slightly slower than 3 times 10 to the 8th, but not enough that we even bother with it. But the fact that water says 1.33, what it tells me is that the speed of light in a vacuum is 1.33 times faster than the speed of light in water. So what you're going to always find is these n values are always going to be larger than 1 because you can't go faster than the speed of light in a vacuum. So the v on the bottom can't be larger than the speed of light in a vacuum. So that's what these numbers are dealing with. Now, the reason why that's important is there's a scientist. This scientist is by the name of Willebrord Snellius. He's actually a Dutch astronomer from 1580 to 1626, and he developed what is known now as Snell's law. Now, interestingly enough, if you look historically, Snellius did not actually come up with it. If you go back, we have people such as Ptolemy came up with the concept. We have Ahadnsen from Egypt and from Greece. We have a Persian scientist in Baghdad who came up with a concept. We have an English scientist by the name of Thomas Hariot. We have René Descartes. We have Pierre de Fermat. So a lot of them have actually come up with this idea, but we name it after Snell because he's another one that kind of derived it. It remained unpublished during his lifetime, unfortunately, but we kind of give credit to him, even though there's a number of other people that can probably get the same credit. So what Snell's law says, using this concept of the index of refraction, is if you take the index of refraction for a material times the sine of the angle that it makes with this interface and the normal to that interface. So in this particular case, if I took the index of refraction of air and I multiplied it by the sine of this angle, theta 1, it should equal the index of refraction in the other material, the material it's getting refracted into, times the sine of that angle. And this is what's known as Snell's law. What it does is it relates theta 1 to theta 2, these incident light and this refracted light that you have going on here. Now, interestingly enough, this picture down here, which I kind of pulled from your book, actually both of them I pulled from your book, kind of shows that it actually doesn't matter whether it's the incident ray on the outside and then bending into the water, or if the incident ray is actually on the inside and then going to the outside, you'll actually get the same result. So if the incident ray happened to be, if we had a flashlight in the water itself and we shine light towards the interface between the water and the air, this would now be theta 1, and then what you would find is you would actually find that the light would refract in this particular direction. Now, interestingly enough, one of the key things that you can see from this picture is the smaller your index of refraction, the larger your angle has to be so that this product will actually come out. So if I have light going from air into water, for example, where it goes from a smaller index of refraction to a larger index of refraction, it will actually bend toward the normal. In other words, theta 2 is going to be smaller than theta 1. However, if you go from a material where the index of refraction is larger than what you're refracted into, it'll actually bend away from the normal. So if I'm going from water into air, I'm actually going to find that my theta 2 is going to be larger than theta 1. So here, theta 2 is greater than theta 1, whereas up here, we actually find that theta 1 is greater than theta 2. So it has to do with which way you're going. The neat thing with this one is if you actually have light going from index of refraction to something that is a smaller index of refraction, it's getting bent away. It is possible if I make this angle even larger, in other words, if I put my flashlight somewhere over here and I shine the light, that it'll hit at such a large angle that it'll actually cause this index of refraction or this angle of refraction to bend, so it'll actually bend parallel to the surface. Or if you get it large enough, it might actually come back in and you get what is called total internal reflection, but it's actually due to refraction. It's actually refracting away from that normal, but that only happens if you go from something larger into something smaller. So these are our two key ideas, the index of refraction being the speed of light in a vacuum. So that's going to be our 3 times 10 to the 8th meters per second divided by the speed in that particular material, because c is always the speed of light in a vacuum. And then Snell's law over here, this fact that the product of your index of refraction, the sine of the angle, is always equal to the product of your index of refraction, the sine of an angle. We'll kind of extend the idea of refraction as we get into talking about lenses and how they work, just like we went from reflection and talked about curved mirrors and mirrors in general. Hope you enjoyed this edition of the Henstitute, and we'll talk more later.